Ever get the feeling we're missing a big chunk of, well, everything? We're diving into the invisible universe today with dark matter, something you clearly find fascinating. Thanks for sending this article in. It's going to be fun to unpack.
It really is a mind-bending concept, isn't it? The idea that the majority of the universe is made of something we can't even see.
It's like the ultimate cosmic hide-and-seek game. But here's the thing. We know it's there, lurking just beyond our vision. And it all started with astronomers scratching their heads over some seriously wonky galaxy behavior.
It's true. The mystery unraveled like a cosmic detective story. Take Fritz Zwicky in the 1930s, for instance. He was studying the Coma Cluster, a massive gathering of galaxies. And he realized they were moving far too quickly for their own good.
It's like watching a car zoom around a racetrack on invisible wheels. Way too fast for the amount of visible matter. Stars, gas, the usual suspects. There had to be something else holding it all together.
And that's just the first clue. Decades later, Vera Rubin comes along. She's observing how spiral galaxies rotate. And what she finds throws another wrench in our understanding of gravity. The stars on the outskirts of these galaxies were moving way too fast. Imagine a merry-go-round where the outer horses are keeping pace with the inner ones.
Defying the laws of physics as we know them.
So, we're talking two separate astronomers, different decades, different types of galaxies. Yet the same baffling problem. There's just not enough visible stuff to account for the gravitational pull that's obviously at work.
And that's where dark matter enters the scene. We can't see it directly, but its gravitational influence is undeniable. It's like an invisible hand shaping the cosmic dance of galaxies.
Okay, so the universe is playing a cosmic prank on us. Fine. But what is this dark matter? Give us something to work with here.
If only it were that easy. We've gotten pretty good at defining what it's not, but pinning down its true nature is like trying to catch a shadow.
Sounds frustrating. So what do we know? What are we dealing with? Well, we know it doesn't interact with light, or at least not in any way we can currently detect. Hence the name dark matter. It's like a phantom, only revealing itself through its gravitational effects.
Spooky. But I did read that scientists have some prime suspects.
Oh, absolutely. One of the leading candidates are WIMPs, which stands for Weakly Interacting Massive Particles. Picture particles much heavier than the protons and neutrons that make up ordinary matter, but with a catch, they barely interact with anything, even themselves.
They're massive, but they just kind of ghost through everything.
Exactly. Their interactions with regular matter, or even each other, are incredibly rare, making them tremendously difficult to detect. But if they exist, they could explain a lot about how the universe behaves.
All right, so WIMPs, elusive heavyweights. What else? The article mentions something even weirder, axions, right?
Ah, yes, axions. Now, these are even more bizarre. Imagine a particle almost massless, but potentially abundant throughout the universe. They were initially proposed to solve a different problem in particle physics, but intriguingly, they could also fit the bill for dark matter.
Okay, so we have these hypothetical particles, WIMPs and axions, that might hold the keys to the dark matter mystery. But it sounds like the possibilities don't end there. It's like the cosmic lineup is getting weirder and weirder. So beyond WIMPs and axions, what else could be lurking out there?
There are even wilder theories out there. For instance, some scientists propose the existence of sterile neutrinos. These hypothetical particles would interact with the rest of the universe even less than WIMPs. Talk about a cosmic wallflower.
Okay, so we've got ghostly particles barely interacting with anything. What else could possibly be on the table?
Then there's the idea of machos, massive astrophysical compact Halley objects.
Machos. I've got to admit, that's a pretty cool acronym for something lurking in the dark corners of galaxies.
It is a bit of a mouthful, but it gets the point across. Machos would be objects made of ordinary matter. Think black holes, neutron stars, or even faint failed stars known as brown dwarfs.
So, instead of exotic particles, dark matter could be made up of these cosmic heavyweights, just hiding in plain sight.
Precisely. They wouldn't emit much light, making them extremely difficult to detect. It's a fascinating possibility, though it's important to note that current observations make it seem less likely than the particle explanation.
All right, so we've got a whole lineup of suspects, but no smoking gun just yet. This is like trying to catch a thief in the middle of the night in a pitch-black room.
So how do scientists even begin to search for something invisible?
That's the million-dollar question, isn't it? It's a formidable challenge. But scientists have developed some pretty ingenious methods. Think of it as a cosmic detective's toolkit, each tool designed to shed light on this invisible realm.
I'm intrigued. Let's dive into that toolkit. What's the first method?
One approach is to look for dark matter's gravitational fingerprints on the things we can see. Just like the wind reveals itself by rustling leaves or pushing sailboats, dark matter's gravity leaves its mark on the cosmos.
So, we can't see the wind itself, but we can see its effects. I like
Yeah.
it. So, how does dark matter's gravity betray its presence? One way is by observing the rotation of galaxies. Remember those weirdly fast-moving stars in the outer regions? Well, the distribution of dark matter within a galaxy affects how fast those stars should be moving. By analyzing those speeds, we can map out the invisible scaffolding of dark matter holding those galaxies together.
So it's like dark matter is the conductor, and the stars are dancing to its gravitational tune. What other fingerprints is it leaving behind?
Another telltale sign is gravitational lensing. Imagine light traveling from a distant galaxy towards us now. Picture a clump of dark matter sitting between that galaxy and Earth.
Okay, I'm picturing it. What happens next?
That dark matter's gravity is strong enough to actually bend the path of light as it passes by. It's like placing a magnifying glass in front of a candle. The light bends around the object, distorting the image we see.
So we're talking distorted images of distant galaxies. A pretty cool way to see something invisible. But what about trying to detect dark matter directly? Is that even possible?
That's the holy grail of dark matter research. And while it's incredibly challenging, scientists are hard at work trying to do just that. Imagine building a trap so sensitive it could detect a single snowflake landing on a football field from miles away. That's the level of precision we're talking about.
That's mind-boggling. What do these dark matter detectors actually look like?
They're often located deep underground, shielded from all the cosmic noise happening on the surface. These detectors are filled with extremely pure materials, carefully chosen to maximize the chances of a dark matter particle interacting with them.
It's like waiting for that one. Incredibly rare moment when a dark matter particle bumps into something and gives itself away.
Exactly, and if that interaction does occur, it would release a tiny amount of energy, which these super-sensitive detectors are designed to pick up.
Okay, so we've got cosmic stakeouts happening underground, waiting for that telltale blip on the radar. What other tools are in our cosmic detectives kit? The article mentions something about smashing particles together.
Ah, yes, collider experiments. This is where things get really interesting. The Large Hadron Collider, or LHC, is the superstar of this approach. It's like a giant demolition derby for subatomic particles.
So we're talking about smashing things together at incredibly high speeds, hoping to create dark matter in the process.
Exactly. The idea is that if we can generate enough energy in these collisions, we might be able to create particles that don't exist in the everyday universe, including potentially dark matter particles.
Okay, I'm following. But if these dark matter particles are so elusive, how would we even know if we created them in a collider?
That's the clever part. Even if we can't directly see the dark matter produced, we can infer its presence by carefully measuring the energy and momentum of the particles before and after a collision.
So it's like figuring out someone robbed a bank by noticing the cash is missing, even if you didn't see the robber themselves.
Precisely. If we see energy or momentum mysteriously vanish after a collision, it could be a sign that dark matter was created and slipped away undetected.
That's some serious detective work. So we've got astronomers playing cosmic detective, using gravity as their guide, and we've got particle physicists smashing things together to unlock the secrets of the universe. I have to say, this deep dive is already blowing my mind. But before we get too far, let's take a step back. Why does all of this even matter? Why should we care about something invisible and seemingly so intangible like dark matter?
That's a great question. You see, dark matter isn't just some cosmic curiosity. It plays a crucial role in the grand story of our universe, especially when we're talking about how galaxies themselves formed.
Okay, I'm intrigued. Take us back to the beginning.
Think about the early universe, just after the Big Bang. It was a chaotic, scorching hot soup of particles.
I'm picturing a cosmic primordial soup, bubbling away with energy.
Now imagine dark matter in this soup. It doesn't interact with light, remember? So while ordinary matter is bouncing around, interacting with radiation, dark matter is already starting to clump together under its own gravity, like invisible seeds in the cosmic soup.
So, even in those earliest moments, dark matter is already starting to shape the universe.
Precisely. These clumps of dark matter grow larger and larger over time, forming a kind of invisible scaffolding or cosmic web.
A cosmic web. You've piqued my interest. Tell me more.
This web, woven from dark matter, creates regions of higher gravity, pulling in the ordinary matter, the hydrogen and helium gas that will eventually become stars and galaxies.
So, without dark matter acting as this gravitational glue, Galaxies might never have formed.
Exactly. It's a pretty mind-blowing thought. Without dark matter, our universe might still be a diffuse soup of particles with no stars, no planets, and certainly no us to ponder its mysteries.
Wow. So dark matter really is calling the shots, even though we can't see it. It's like the invisible hand shaping the universe as we know it.
And here's where it gets even more fascinating. We can actually see the influence of this cosmic web, this invisible scaffolding, in the cosmic microwave background radiation.
The CMB.
Oh, yeah.
It's like the baby picture of the universe, right? Taken just a few 100,000 years after the Big Bang.
Exactly. And what's amazing is that this baby picture contains subtle temperature fluctuations, tiny variations in the early universe's temperature. These fluctuations are like echoes of the density variations present shortly after the Big Bang.
Okay, I'm following. So how does this tie back to dark matter?
Well, those temperature variations, those density ripples in the early universe, they align perfectly with the distribution of dark matter predicted by our models. It's like looking at a map of the early universe and seeing the blueprint for the cosmic web already laid out, with dark matter as the architect.
So even in the universe's baby picture, dark matter's influence is there. But I have to ask, with a mystery this big, there have to be some doubters, right? People who think maybe we've got it all wrong.
Well, there are.
It's like we're trying to build a puzzle where most of the pieces are invisible. It makes you wonder if maybe there's a simpler explanation we're missing.
You're absolutely right. Questioning our assumptions is a vital part of the scientific process, and there are alternative theories out there. One of the most prominent ones is called MOND, Modified Newtonian Dynamics.
MOND. It's like saying, hey, maybe Newton didn't have it quite right after all. So what's the basic idea behind it?
Essentially, MOND proposes that gravity doesn't behave exactly as we expect at extremely large distances, like the scales of galaxies and galaxy clusters. Instead of invoking dark matter, MOND suggests that our understanding of gravity needs a little tweaking.
So it's like saying, maybe we don't need this whole invisible matter thing. Maybe gravity just works a bit differently than we thought. Does that idea hold up? Does it explain the observations as well as dark matter does?
It's a complex issue, and like any good scientific theory, MOND has had its share of successes and challenges. It's quite successful at explaining the rotation curves of individual galaxies, that puzzling behavior that first hinted at dark matter's existence.
So it scored some points right off the bat, but it sounds like there are some catches.
Yes. While MOND does well with individual galaxies, it faces hurdles when it comes to explaining things on larger scales. For instance, it struggles to account for the motions of galaxies within clusters or the patterns we observe in the cosmic microwave background.
So, like a good detective story, there are always more clues to consider, more pieces to fit into the puzzle.
Exactly. Right now, dark matter, elusive as it is, seems to provide the most comprehensive explanation for the wide array of observations we have. But that doesn't mean alternative theories like MOND should be dismissed. They encourage us to keep questioning, keep refining our models, and keep searching for an even deeper understanding of the universe.
And who knows? Maybe someday we'll find a theory that elegantly ties everything together. It's like we're standing at the edge of the unknown. And every new observation, every new experiment is pushing us further into that uncharted territory.
It's truly an exciting time to be exploring these cosmic mysteries, and who knows what incredible discoveries await us. Perhaps we'll uncover new particles, new forces, or even entirely new branches of physics we haven't even dreamed of.
It's mind-blowing to think about. We started with some unusually fast-spinning galaxies and ended up on the verge of potentially rewriting our understanding of the universe. What a journey. I have to hand it to you, listeners. You sent in an article that sparked one incredible deep dive.
It's a testament to the endless wonder of the cosmos and the power of curiosity.
Exactly. So if this deep dive left you wanting more, and I have a feeling it did, you're in luck. We've got links to more information about dark matter, WIMPs, axions, even those intriguing machos in the show notes. Trust me, there's a whole universe of fascinating information waiting to be explored.
And until next time, keep looking up at the stars and never stop asking those big cosmic questions. You never know what amazing discoveries await just beyond the horizon of our understanding.